in the correct function. It needs to be in radians or degrees, depending on what you're using. When you deal with any kind of trigonomic function, so sine, cosine, tangent, if your calculator is in degrees, it's expecting the input to be in degrees. If your calculator is in radians, it's expecting a value to be in radians. So this will give you two different sets of numbers if you put the value in incorrectly. 90% of the stuff we're going to deal with is going to be in degrees. Make sure your calculator is in degrees. A lot of the scientific calculators, they default to radians, which I don't understand why, because most of the stuff we do is in degrees. There's 2 pi radians in a full circle. There's 360 degrees in a full circle. That's one of the things we're going to be talking about today. Make sure you have your calculator. If you don't know how to get in there, there should be an option somewhere on there that says mode or options or something like that. When you click on it, it'll pull up the all options. You want to make sure you have there's a radian or degree button selected. Make sure it's in degrees. Some calculators will have a little indicator that'll show you that it's in degrees while it's running. Like the TI-83, it just does it in the background software. So make sure you have your degree or your calculator in the correct format for what you're using. Otherwise, you'll have to apply these conversions to solve for them. Any questions about that? Okay. So when we are looking at a graph of a circle, when we graph, we're going to be basically starting from this point. We're going to move counterclockwise for positive degrees. We're going to move clockwise for negative degrees. So with this starting point here, we have 0 degrees. We have 0 radians. We're starting at 0. The idea behind the circle is this is how motors work. We are spinning something. And in the process, we're spinning a shaft that has either magnets or coils of wire. As we spin these magnets or the coils of wire, depending on what it is, we have other magnets out here, and as we turn them, this is how we generate AC. It's very, very easy to generate AC signals. And so what we're going to reference these guys is the degree of travel, basically. So in a sine wave, if we go all the way around the circle, we have 360 degrees, or 2 pi. So what we need to understand is how far around the circle are we traveling when we're given some sort of a value. If we've gone 45 degrees, where are we? Yep. So, well, what if we've gone 45 degrees? Where's that at? This way. Yeah, 45 degrees. Okay? 45 is a pretty common value in electronics. That's one of our markers. Okay, another common that we have is at 90 degrees. We have 180, 270, and 360. Primarily what we use, we're going to use the 45s, not much more of the 45 over 90 degrees. So 45, 90, 180, 270 we'll use a little bit, but not a whole lot. And then 360 is the other primary one that we need to know. So if our full circle is 2 pi and 360 degrees, when we come to the half circle, it's 180 degrees or 1 pi. Okay, our calculators have this function built into it. So you don't have to type in 3.14. You can just hit the pi option. And honestly, I would carry it out 3 or 4 digits anyway when you're doing calculations. So when you're using pi, instead of just using 3.14, use 3.1415. Your answers will become a lot more accurate because remember, we want to go out 3 decimal places for our accuracy. So at 90 degrees, if 180 degrees is pi, 90 degrees is half pi or pi over 2. 270 degrees is 3 pi over 4. 1.5 pi, basically. So, 2 pi over 2? 3 pi over 2, yes. Those are the 45s or the fourths. All right, so how do we convert these guys? Because like I said, the 90, the 180, the 270, those are easy to calculate. Well, what if I wanted to know how many radians was in 74 degrees? Okay. So what we need to do, so remember, there's 360 degrees in 2 pi radians. Okay? This is our conversion. We can simplify this down to go to 180 degrees is over pi. Again, we want to use the more simple values. So if we're wanting to go from degrees to radians, we have 74 degrees is X number of radians. Our conversion is 180 degrees over pi radians. Okay? So now we just solve for our X number of radians. So we end up with 74 times pi is equal to 180 times X. We divide this over. So 74 pi over 180 is equal to X. And just like Dylan said, we're going to divide by 180 pi, which we'll invert and multiply. So in this case, 74 goes into 180 how many times? Well, depending on how we want the answer. There's going to be times where we want the answer in pi radians. There's going to be other times where we just want the full number. So, yeah, we'll solve for that first. So 74 by 180. Okay, which this is going to reduce down to 37 pi over 90, or if we were just looking for a value, then we would multiply the 3.1415 in there. $1.2915. So 1.215 radians or 37 pi over 90. Again, just depending on how the answer is asking for it. If it wants it in pi, it'll give you the symbol afterwards. Most of the time when we're solving stuff, we're going to bring it all the way down till we have a decimal number, because that's how we operate, is using decimal numbers. We don't have pi just floating around. Yeah. Okay. So what if I wanted to go from 2.5 radians, and I want to convert that into some number of degrees. First thing we're going to do, we have 2.5 radians divided by X number of degrees is equal to pi radians over 180. So again, when we do our conversions, we want to put, make sure they're in the same order. Radians per degrees, radians per degrees. And then we solve. So we have the 2.5 radians times 180 is equal to pi times X degrees, We divide both sides by pi. And that will give us our value. Do what? No. The only time you need to have your calculator in degrees or radians is when you're doing trigonometric functions. Because it's assuming the value you put in there is radians. 2.5 radians is something completely different than degrees. Okay? What does this answer come out to be? How much? 1, 2, 3? Sorry, this fan up here makes it hard for me to hear sometimes. Okay? So if we were to punch in our calculator at 2.5, and we were thinking it's in radians, or if we think it's in radians, but our calculator is set to degrees, it's going to assume 2.5 degrees, where we wanted 143 degrees. So either way, we can punch these values into our calculators. We just have to make sure what we're putting in is what the calculator thinks we're putting in. So in the end, our conversions that we have, so if we're going from, let's see, degrees, so degrees to radians, we're going to take our number of degrees times pi, divide it by 180. If we want to go from radians to degrees, we're going to take the number of radians times 180 and multiply and divide it by pi. So there's our conversions. Again, a lot of the stuff of what we do is going to be dealing with degrees more so than radians. Once you get into calculus, I think, that's kind of where the switch is too, is it uses them pretty equally, I believe, between radians and degrees. And it's hard to keep track. Any questions about these? In the quizzes, it will remind you about these formulas, so it'll still have those at the top of the quizzes for you to do. The next part we want to talk about is called angular velocity. So angular velocity is a reference to how fast are we traveling as we rotate something. Okay? We have a frequency. Frequency is measured in hertz. What is the frequency? If I say something is going 60 hertz, what's its speed? What are we talking about? Wavelengths. We can calculate the wavelengths from those. How often something happens. If I have something occurring at 60 hertz, it's 60 cycles per second. Okay, the frequency of cars. We could measure the frequency of cars driving through on Martin Luther King Drive over here in hertz. The number of cars per second. Now, granted, with this being a road in the middle of campus, that count better be 1 or 2 hertz at the most. Because if we got 50 cars flying through here a second, somebody's going to get hit. Okay? So depending on what you're looking at, having a high frequency is good or having a low frequency is good. In electronics, a lot of what we do later on, 4th semester, things like that, is high frequency. Gigahertz, megahertz, terahertz, speeds. Speeds for internet. We're talking gigabyte downloads. We're talking, terabytes of information being sent. How long is it going to take to send a terabyte of information when we have a, 9600K bits per second connection? Quite a bit. Okay, how long? Do you guys know what the 9600 kilobytes per second is? That's modem speed. That's the old dial-up. That was internet speeds back in the day. No, back in the day was like 15 years ago. Yeah, 96,000 bytes a second was the connection. Okay, how much information is in a picture? So much.
My camera has 108 megapixels.
Yeah. So this little picture, if I can get it to load. That guy. That little background picture. Okay, that file is 6.12 kilobytes. So that little picture would actually load relatively fast. You got 6,000 bytes. It would take it about a second to load. Okay? Nowadays, we want a second to load images like that. And we want these images to load at 24 frames per second. If you're playing video games, what kind of a frame rate do you want? 60. So or 200. You want at least 60 frames a second. So you're getting 60 of these pictures every single second. That picture is 65K. Yeah. So if we have 65K, so 65,000 times 60 frames a second, that's 3.9 megabits of information in 1 second. So the rate of transfers is really important. And the reason we're talking about these is when we get into these values. Where's my mouse? We're looking at our angular velocity. So we have the frequency. How often is things happening? But more importantly, how much is this thing moving according to our frequencies? So, as like we said before, if we were to go in a full rotation, that is 360 degrees. Okay? If I'm making 60 rotations per second, how many degrees am I traveling? 21.6K. So all angular velocity is, it's your frequency multiplied by the degrees it can travel. That's it. That's all angular velocity is we want to know how many degrees are we traveling based on how fast our speed is. What's funny is it gives you the formulas too. Yep, W is our angular velocity. It's measured in degrees per second. Radians. Rads per second. This is different than if we're getting exposed to radiation. These are good rads compared to the radiation rads. And we can work either direction. We can be given how far we traveled, and we can try to solve for what is the frequency that we're moving at. Basically how fast are we going? Okay? The reason that we want to know this is when we get into motor controls. Because we're working with stepper motors, we want it to go to a specific position every single time. So when something happens, or think of it with a robot arm. We want it every second to reach over, catch a pie, move it over, and set it on the conveyor belt to get it going. If we're not back in this position every second, what's going to happen? Yeah, we're going to drop pie on the ground, and it's going to be a huge mess. And every single time it misses one, we're going to, us or somebody else is going to have to come in and clean it up. Because usually you have a whole bunch of equipment in one spot, and when something breaks or gets goopy, it spreads, especially if there's moving components. I've seen videos of different factories where something wasn't there that was supposed to be and their sensors didn't catch it, or something broke in the mid-machine. Like they had a pie, maybe it came over at like 1.2 seconds. So it didn't quite set on where it was supposed to. So when it brings it over and sets it down to the next station, it's dropping the filling here, but the pie shifted over a little bit, so it only gets half the pie filling. Okay? That's why this is important, because we want to know what's the speed that we can travel so we can know how long we have to tell it to move for before we tell it to stop.
And it's like half the bag every time.
Mm-hmm. Well, but see, here's the thing. They're measuring it by weight, not by how much it fills up the bag. Yep. And the other thing is too, and there's a reason why they have air in those bags. It's to keep them from getting crushed. It gives it a little bit of padding so the bag won't compact down so far. Yep.
That's what they do wrong, is when they package it, supposed to pressurize it to a certain altitude. I worked for a shipping company that did lots of food processing, maybe sending stuff that was pressurized, and they would send it up into the mountain, and it would explode when it gets there. So,
Yeah.
overpressure.
Yeah. But again, and things like that, that's something they'd be like, okay, if we're shipping up into the mountains, we need to make sure we decrease this. So we have part of our line going off. Again, every third bag it's going to grab and move it to a separate line to change the pressure. Again, it all comes down to timing. How much are we going to move at what speed? Because things are going to be moving in degrees a second. You're going to be wanting, information being traveled and things like that. Another way to look at this is with the frequency of a waveform. If we have a waveform coming into one of our chips to telling it to do something, and we need to be able to move, we have to make sure our motors can handle it. Can they handle moving at 6,000 RPM, or basically 6,000 degrees a second for a year? Some motors can. Some do that constantly, and some are very good at it. Some motors you buy, they can't. And so as you're pushing them to the limit, that's the other part you have to take in consideration. Will this part survive? When you're troubleshooting, when you're prototyping, when you're designing things, that's not nearly as important as trying to get the idea to work. Once you get it working, then you can refine it and make it better. That's also kind of the idea with the projects that we have in sixth semester. There's projects there. You can work on your own, but you can also take one and refine it, make it better, add more stuff to it. And that's the idea, is we're constantly looking to improve things with either different components or, even different functions, different actions, things like that. I know I use the examples of pies a lot, or those types of machineries. For one, that's what I know. But the other one is, the classes I took, that was kind of the big thing, is I did a lot of what are they called? The PLCs, yeah. I took a class that was just PLCs, which is a different kind of logic, programming, things like that. It's a very mechanical programming. You're activating relays, things like that. And so that was the whole lab, is we had this board that had a bunch of toggle switches and had buttons. And those buttons would light up and they were all controlled by it. And the idea was you had to be able to basically load in this network. So each of these was a station in a pie fit making facility. So you made the crusts, then you had the filling, then you had the top, then you baked it, and then you cooled it. You had to also track if it missed a pie for some reason. Because if for whatever reason there wasn't one in this location, it had to remember that and move that hole through the system and keep track of it. Because when there's no crust, you don't want to dump any of the pie filling in. And you don't want to dump a crust over the top. And then you don't want to have to run it through a full bake cycle. Yeah. Because again, by doing that, by keeping track of this, now you can keep saving energy, because now you're not blasting your furnace at your high temperatures. You can let it run down to an idle state, and then you keep it hot, but you're not burning as much fuel in between. And so, like I said, there's many different options, and that's why I keep those in my mind, because that's what I'm thinking about. That's what I learned in school. That's what I did as a career. Same with any of the robots you guys want to build. It's all going to be based on, go to this point. Well, how fast do you want it to get there? Can your motors handle it? BattleBots, for another example, how fast do you want things to spin versus how much energy they can consume? Exactly. But there's times when you start going too fast, you lose control. And so it's this balancing act. But you want to be able to account for how fast am I going versus how much, how much energy I'm putting into the system. Okay. That's it for this week. And the semester, really, as far as material goes. That's all the information I've got. Isn't this crazy? We've made it all the way through DC. You guys have a very solid understanding of how DC power works. Oh, trust me, you'll be hating me for saying that when we get into next week, because you're like, I don't remember any of this. You didn't tell me how this worked. This is not how DC works. Fun, difficult stuff. There's kind of a limitation to what we can do with DC. AC, it opens up so many more worlds and realms. Sound, video, audio, information, applications. Yeah, this is just the very, very basics. And like I said, we're covering a lot of material. The other semesters, they're going to kind of have the same thing. Second semester, you're going to talk about transistors. You're going to talk about digital. When you get into third semester, now we're going to start taking in, okay, I want this transistors, and I want to be able to manipulate it with capacitors. Okay? Combine those together. Now we're going to take this little chunk and expand it. We're going to grab this little chunk with the digital. We're going to expand this. We're going to grab this and expand it. Fourth semester, it's going to grab things that we're going to cover, like I said, in 3 or 4 weeks with filters. It's going to grab those filters, and it's going to expand that section. We get into sixth semester, and it's going to grab this even more and put everything together underneath a large umbrella. So we cover a lot of information this semester, but the idea is we grab it later semesters and expand it as we go. Okay, does anybody have any questions from this week, from the quizzes, that you would like to cover? Oh, yeah. Do what now? Yeah, last week was just mesh. The test will be over mesh. Do what? Yep. Okay. One thing I did promise. Okay. Okay. This is what we affectionately refer to as triple points. Okay. It is worth your part of your homework grade, but it is not required for the test. Yeah. Okay. So the idea behind this is we're going to turn this on. We're going to have a voltage supply here. We're going to have a voltage supply over here. So the first thing we need to do is we've turned the circuit on. We're going to measure it. What has happened in the circuit since we've turned it on? The capacitor has charged. So our cap is full. When our capacitor is full to DC, what is it? It's an open. So now it's an open.
So now like R1 and R2 are series.
They will be, okay? But there's still going to be a voltage drop here. And it is important to what this capacitor will charge to. Okay? So the very first step, we have to understand that after some time, we don't know how long it's going to be, but when we finally get to measuring the circuit, this cap is going to be fully charged. And the reason we know we're looking at this after time has elapsed, we're not given to say what's happening at this specific time. Okay? So now, the cap is taken care of because it's going to charge to some value. Whatever it has access to, that's going to be what it charges to. Okay? What else do we have in the circuit? A Zener diode. So in the directions, we're given a VZ. We'll just say it's a 3-volt Zener. Okay? The next step we have to do is determine this diode. Is it in forward or reverse bias? Well, yeah. What we're going to do is we're going to pull that guy out of the circuit. Okay. Think Thevenin. Think Thevenin at this point. Okay. So now we're going to pull this diode out, and we want to Thevenize from C to D. Okay. We want to know how much voltage is across this guy. Okay. When we're looking at this, what do we have now at this point? It's a series circuit. We've got a voltage source. We have a voltage source. Are they aiding or opposing each other? They're going to aid because you have negative turning into the positive. Okay? You have resistance in series. What's it going to do? It's going to add together. Now we can go through and we find out what the voltages are with these two components removed and put them into the values and see what we get. Then the idea is we're going to literally go from point C to point D and determine, is this diode in forward or reverse bias? Let's say we had, so you got to check to see if it's forward or reverse, and then you got to see, does the voltage that's available to it match my Zener diode? Okay? If it does, great. If it doesn't, it's a little more interesting because you're going to have more voltage dropped. Okay? So let's say when we go through this, we find out our Zener diode is reverse biased, which is the way it should operate. And it has, let's say we come up and we have, so we got 5 volts, we got 6 volts here, and we got 10 volts here. So if we come around, we're going to be charged like this. Okay? We're going to have a positive 5 volts, we're going to have a negative 10 volts, we're going to have a positive 6 volts. Maybe I should change this one, just for our hypothetical. So we have plus 5, minus 2, plus 6. So that gives us 7, 11 volts. Okay, this guy's reverse bias, so it's going to take 3 volts. Now, it's reverse bias, we have enough voltage, this is going to drop 3. If there's not enough voltage, it's going to drop everything it can. So in this example, it works out great. So we have 3 volts here, we can go through. Now, what we're going to use is mesh. Okay? We have 2 loops. We have an A and a B. Now that we know the voltage of this guy, we can do it. Because before, we had no idea what this voltage was. So we have our A, we have our B. We go through and we solve currents and voltages. We know that's going to be 3 volts. Okay? Then at this point, we just start using nodal analysis. Because we're going to get a current coming here, current coming here, current going this way, current going around, and we'll have some current flow in one of these 2 directions. Then once we have that, we can figure out the current that's going through here the current going through here, we have resistance, we can solve for voltage. Same with these guys, currents, voltages. And then, once we have our diode back in there with its drop, we can solve for the value of our capacitor just by using Kirchhoff's voltage law. We're going from here, walking around, to here. So this one is the culmination of everything that we have done this semester. Thevenin, mesh, diodes, capacitors, series circuits, series aiding, series opposing power supplies. It's got a little bit of everything in it. It even has the parallel portions when we start splitting current at the node to the diode. This is everything that we've learned this semester. All wrapped up in one package. Okay? So here's the idea too. So in this instance, we had enough voltage. But let's say we were back to where I started with this guy. I had said 10 volts. We have plus 5, minus 10, plus 6. That gives us how much voltage? 1 volt. The Zener is going to take all of it. How much voltage will we have across our 3? 0 and 0. Okay, that is a real possibility. Okay, what if we came through and we found out, when we solve for this guy, so remember that the negative part of the diode is here, the positive of the diode is here. What if we come through and we find out, let's say this guy is switched around, and now we have a voltage that goes like this. What's going to happen with that diode? It's only going to drop 0.7. Unless it's a germanium. Unless it specifically says it, assume that it's silicon. I'm not saying that could be an option. I'm not saying that it's not an option. There's always the possibility of these. There's multiple variations of this problem thrown in there with different voltages, different polarities. The diodes turn different directions. It's different. Sometimes it's a Zener, sometimes it's a not. Things like that. Again, it depends on what you're looking for. Like your power supplies, maybe you need to get it up just a little bit higher for your voltage. Use a germanium diode, you're going to have a less voltage drop when you go through your diodes as a bridge. Okay. Try it. Go through it. We can go through an example with this next week as well as a review. You guys will still have access to take the quizzes, take the tests, or not the tests, the quizzes up until Friday of next week. Friday at 5:30. Do what? Yes. Yes. Use them as a study guide. Honestly, if you have a question about what could be on the test, take the quiz. It's not going to negatively affect your grade. I could care less how many times it shows that you've taken this test. I really could. All I care about is, as you're working through these problems, do you get it? Because that's the cool thing I can see too, is everything's time-stamped. So I can see, as you're taking this test, how many times did you start this test over? How many times did you put in answers? Did you get 0, 0, 0? Then your next question, you got like a 35%. Your next one, you got a 45%. The next one, you drop back down to a 15. Okay? The next one, you jump up to an 80, and then you start maintaining 80s. Okay? I can see when the material clicked for you guys. Okay? Not that I care. I do look on those from time to time to see how you guys are doing. I don't mean that rude. Let me rephrase. I do not care how many times you take the test. I care as if you're getting the material to understand it. Between the quizzes and the tests, that's what I care about. And especially now, right now, I can go back and look. Even if you're just getting the quizzes to get the values to work through a problem, that's great. Like I said, it doesn't matter what it gets there. It just matters your highest grade on the quizzes. It is your homework grade, as much work as you want to put into getting that to do it. The way this is set up, for you to maintain, to get a grade, if you get 80s on all the quizzes and you do okay on the tests, you're going to get probably a C plus to a B minus in this class, in all honesty. And if you're getting 80s consistently on quizzes, your test score is going to be in the 80s. Generally. There are exceptions. But the idea here is we're trying to give you guys, we don't want you guys to take a test that you're going to just directly fail at. Okay? That's why those requirements are in place. Is we want you to push you guys so you have an understanding of the material before you test on it. So, again, use this time if you have. The quizzes, retake them, up your scores. It can't hurt. It can only help. 1% might be the difference between an A or a B. In all honesty, it might be. If you're sitting at an 89.5, or if you're sitting anywhere on those thresholds, take the quizzes. Give yourself some buffer points. Also, you can use that if you're sitting at a low A or a low B or a low C or whatever it may be. Go through the quizzes, bump that score up, because then that's an extra couple of points on the final that if you miss, it's not going to drastically affect your grade. Because again, a couple of points difference between a B or a C or an A or a B can make all the difference. So, does that make sense as far as what you're supposed to do? I know I didn't specifically go into the very nitty-gritty, but the idea is your capacitor is going to fully charge, and then it's going to be an open. Your diode, you have to remove and basically Thevenize the voltage at that point. Not the resistance, just the voltage. Find out if your diode, what bias your diode is. If it's a Zener diode, you want it to operate in reverse bias. If it's in reverse bias, how far is it? With a Zener, is it going to take it all? Is there going to be any leftovers? Things like that. And once you get those, then that voltages you'll see split across the rest of the circuit.
So
Yes.
when you Thevenize it, you're going to have two different Thevenin circuits because you've got the upper half and then you've also got the bottom half. So could you?
No, you're going to end up with one circuit, and then the idea is as you go around, you're going to find the voltages across all the resistors, and then it doesn't matter if you go this way or this way. You go from this point to this point. Again, it doesn't matter which direction you go. Yes. Not the whole circuit. Yeah, usually that's what I usually do, is do those two values. You have to find them. Yes, all you're given is your sources, the resistor values, what kind of a diode it is, if it's a Zener or not, and what the rating of it is. And I don't even think you're given a capacitor value, because we don't care about the capacitance value at this point. There's only one capacitor in there. So, again, remove the diode, find out the bias. When you determine the bias, determine the voltage drop that your diode's going to have. Then you use mesh to solve for the individual currents on those sides. And then once you have the currents, then you can solve for all the voltages. They would be. And so, basically at this point, it's a two-loop, two-supply problem. Who's saying that doesn't happen? The guy that wrote this test is now the guy that's teaching second semester. So I'm just saying, he very well could have thrown one in. Okay. Other questions from this week's material?
What's the math base on this test? Is it logs and imaginaries?
Logs and imaginaries and complex, which is the combination of real and imaginary. So, So for the math, there's that problem that we talked about, how to use the logs. So it's to start with simultaneous equations. We have our imaginary values, so it's the values of I, knowing the difference between polar and rectangular. The powers of I.
I get confused by that. I understand the I, but then you start multiplying and I get confused.
I think you just get confused because you see class and you.
Bro, I started like 20, 30 minutes.
So as far as what these go, the pattern.
So I understand the pattern.
Okay.
It's like I always get 8 out of 10 on that quiz, and then the last two that are like multiplying within it.
Okay.
I just guess on those.
So the idea on this one, so I to the 0 is what? 1. Anything to the 0 power is 1. I to the first is I. Okay, I squared is -1. I3 is -1. So the idea behind this is I to the third is the same as I squared times I. Because remember at the very beginning when we're talking about multiplying powers together, if it's the same base, you have a value. When you multiply exponents, they're just going to add. So what we're doing is we're just trying to reduce this guy down to easy to manage values. So like here, if we wanted to go j to the 200, is this kind of the idea that you were thinking of?
Like what's in the other side, like the 85 plus j to the 30.
Okay. So these are complex numbers. So that's the next spot. The idea behind this is we have real values, we have resistance values. So the way to think about it is this is resistance, and this is resistance that's coming from a capacitor. Okay, they're two separate things. The one with the capacitor, we cannot physically measure. It exists, but we can't measure it. We can measure the effects of it, but not that value itself. And so we have to keep those guys separate. We cannot add them together. We can add them together with Pythagorean's theorem and trig, but we can't do it just normally. So the idea here is we're going to combine or multiply these guys together in such a way that the real values will add together, the imaginary values will add together. So if we have any j values, we can combine those together into one value. But we can't directly combine them together with the real values. Like we said, think of them as water and oil. Okay? We can't mix. So 85 units of water, 30 units of oil. We're going to add that to another 85 units of water and 30 units of oil. When we mix them together, we get the 170 units of water and 60 units of oil. And we'll see that those are separated. But what we do is when we combine them together using Pythagorean's theorem, think of it as now we're turning it into a dough. Okay? Now they're coming together to form a useful function. If that kind of makes sense.
So you can simplify like the J60 down, it's like multiples of 4 and stuff like that. But the 85 just stays whatever that multiplies to. It doesn't simplify.
Well, it will. That one came out to be, we didn't finish that one, but yeah, the 85 squared comes out to be whatever 85 squared is.
And that's
You're done with that value. So in this one, when we're multiplying guys together, remember we're going to FOIL. So we're going to take our first number and we're going to multiply it by everything in the second value. Take the second number, multiply it by everything in there, and then combine everything together. So we end up with an 85 squared. We end up with a plus J30 and a plus J30 times 85. And then we also end up with the J squares multiplied together. So J times J is J squared, right? Well, what is the J squared in imaginary values? -1. So then this value becomes a -900. The J goes away. And then we still have two real numbers that we have to combine together. So the simplest form is we want to get it down to where we have one real value, one imaginary number. That's it.
so the times. I think my issue was I was simplifying in the 30s. Like I was misreading, so I was like taking the root of 4 out of the 30.
Mm-hmm.
That's what I was doing.
Okay. Okay. Let's see, imaginary numbers, logs, remember, you have your base to an x is equal to some value, is your exponential form. The log of that is log of whatever base you had times your answer, your argument, is equal to your exponent. Logs, all we use is to grab that exponent and move it down so we can manipulate it. Any other questions? Okay. If you guys do not have any other questions, at least for the class, you are excused. Have a good weekend. Get your assignments and everything done and turned in. If you do have further questions, feel free to stick around. I can still help you guys out. So